integration rules. So we're just applying a lot of the basic integration rules you've already learned to some integrals that may not look like those integration rules apply to them. So we're going to use some ways to manipulate those integrals to make them look like what you've seen before. So, for example, our first example here is to find the integral of three different integrals, and they look very similar. The difference here is that our numerator increases by degree each time. So we have a constant for a, 4x for b, and 4x squared for c, while the denominator remains x squared plus 9. So the first one is quite simple. So if I look at this, I have 4 over x squared plus 9 dx, and I can rewrite that as 4 on the outside, and then 1 over x squared plus 3 squared. And then if I look on that cheat sheet of integration and derivative rules that is posted on Schoology, I can see that this follows the arctan rule. So then I'm just going to get that constant of 4, and the a value is 3. So I get 4 over 3 arctan of x over a, so x over 3 plus c. My second integral here is 4x over x squared plus 9. I noticed that if I let u equal x squared plus 9, then the derivative of that is going to be 2x, which then will cancel the x in the numerator. So u substitution is going to be an excellent candidate for this. So then I have that dx is going to equal du over 2x. So when I put my substitution back in, I have 4x over u times du over 2x. So then I'm just going to have an integral of 2 over u du, which then will be 2 times the natural log of the absolute value of u plus c. Substitute back in my u, and I don't need I don't need absolute value anymore because x squared plus 9 can never be negative. All right, so then my last integral is a little different. So my last integral here, I have the same degree. So u substitution isn't going to be helpful here because nothing's going to cancel. So if I think about ways to manipulate this to maybe make it look like something that is on the list of integrals, an option here is I still have that x squared plus 3x in the denominator. So what I might try and do is I might try and break this up into two separate fractions. And so how I can do that is using long division. So if I actually take that 4x squared and divide it by x squared plus 9, then I'm going to get, let's see here, 4, and then I'll get 4x squared plus 36, and then subtract all of that. I'm going to get a negative 36 remainder. So now I can rewrite that fraction as a whole number, 4, plus the remainder, negative 36, over the denominator, x squared plus 9. And so now I see that my first integral just becomes that 4x, and my second integral is that arctan that I already had in the first one. Oops, I messed up. All right, so it's negative 36 times and then 1/3 arctan of x over 3 plus c, and then go ahead and combine that negative 36 and 1/3. Okay, so there are some simple examples of how you might have similar looking integrals with completely different ways to solve them. Okay, we're just going to keep going on with some different integrals. So our next one is if I have x plus 3 over the square root of 4 minus x squared. So this one, once again, we're going to split it up into two different integrals or two different fractions, but I have addition in the numerator, so I'm going to use that to my advantage. So what I'm going to do here is I'm going to say 0 to 1 of x over square root of 4 minus x squared dx plus the integral of 0 to 1 of 3 over the square root of 4 minus x squared dx. And so how that's going to help us is on the first integral, I can do some u substitution. So for this one, I'm going to let u equal 4 minus x squared. So then du dx is going to equal negative 2x, and then dx is going to equal du over negative 2x. So then when I go through and do this, I'm going to get, okay, so 0 over 1, x over square root of u times du over negative 2x. And so then my x's here will cancel, which is fantastic. Great. Okay, and let's move on to my second integral. My second integral, well, if I look at this, this follows the arc sine rule. So I have my a value is 3, or sorry, my constant is 3, and I have 1 over square root of 2 squared minus x squared dx. So then I'm going to get my first integral. Sorry, I'm just kind of jumping between them so that they're in order. So remember, oops, I forgot to do something important. So when you use u substitution, remember your bounds now are still in terms of x. So it's really important to write x equals in front of those so that you remember that those are not in terms of u, so you're not quite ready to plug them in right away. All right, so let's look at our integral now. So our integral now is x equals 0 to x equals 1. And we have negative 1/2 of u to the negative 1/2 du. And then over here, I have that arc sine. So I have 3 times the arc sine of x over 2. And that is evaluated from 0 to 1. Over here now, I can say, oh, well, you could do u substitution, or you could, think about the anti-power rule. And I have negative u to the negative, or sorry, not negative 1/2, positive 1/2. Negative u to the positive 1/2, evaluated from x equals 0 to x equals 1. And then if I want to go ahead and plug in my bounds for my next integral, I get 3 arc sine of 1/2 minus 3 arc sine of 0. And then over here, I'm going to then go ahead and plug in my u value. So I have the square root of 4 minus x squared, negative of that, 0 to 1. And now I don't need to write x equals because everything is in terms of x. And then arc sine of 1/2 is pi over 6. And arc sine of 0 is 0. So 3 times pi over 6 is pi over 2 minus 0. So then when I plug in 1 into this, I'm going to get negative square root of 3 minus, and then 0 square root of 4 is 2, so a negative 2, and plus pi over 2. So my final answer, if I plug this into a calculator, is approximately 1.839. Here's a nice little graph of that. So that area here we just found is about 1.839. Okay, and you can check this on your calculator, which is a fantastic strategy for definite intervals.